Welcome back to another deep dive. We are so glad you're here with us today.
Yeah, really excited to get into this one.
So, I want you to picture a scenario for a second. You are sitting in, say, seat 12F on a commercial flight.
Window seat, obviously.
Obviously, right. So you've got your headphones on, you're looking out the window, and suddenly the plane starts descending into this incredibly thick, just impenetrable layer of gray clouds.
Oh yeah, where you can't even see the wingtip.
Exactly. You can't see the wingtip, let alone the ground. But you aren't panicking. You just take a sip of your coffee and you trust that the plane knows exactly where it's going.
Because it does.
Right. You don't think about the invisible signals that are guiding hundreds of tons of metal safely to a runway you can't even see. You just trust that the infrastructure works.
It's a really profound level of trust when you actually break it down. I mean, we place our lives in the hands of these invisible mathematical systems every single day without a second thought.
We really do. And today, we are going to look at the blueprint of a man who spent 50 years acting as the silent architect of those skies.
Yeah, we have a stack of documents detailing the professional resume of Dumar Omar Ramírez, who is a Venezuelan electronic engineer and aerospace specialist.
But we aren't just going to, read through a CV today. We are looking at the anatomy of invisible infrastructure. How is it built? How is it protected? And, what does it actually take to maintain it flawlessly for half a century?
What's fascinating here is that a career spanning 5 decades in aerospace and government telecommunications, well, it provides a perfect lens to examine exactly how these safety-critical systems actually function.
Right.
We are looking at the engineering of certainty. I mean, when you dive into these sources, you see this masterclass in designing infrastructure
Yeah.
that absolutely cannot fail.
No room for error.
None. And perhaps more importantly, designing administrative processes that are just as bulletproof as the technology itself.
So let's start with the technology itself. What I like to think of as the invisible hand that makes all of modern air travel possible.
I like that phrase, the invisible hand.
Thanks. So the sources highlight his expertise in radio navigation and radar systems. And immediately, we are hit with just an absolute alphabet soup of acronyms.
Oh yeah, VOR, DME, NDB, ILS.
Right, exactly.
Yeah.
So if we are going to understand the blueprint of his career, we need to decode these. Okay, let's unpack this. What exactly are these systems doing in the sky?
Let's break them down because they really are the fundamental building blocks of aerospace navigation. Let's start with VOR and DME, which they usually work together.
Okay.
So VOR stands for Very High Frequency Omnidirectional Range.
Which is a massive mouthful.
It really is. But conceptually, it's actually quite simple. Imagine a massive invisible lighthouse on the ground.
Okay, lighthouse.
But instead of just sweeping a single beam of light around, it broadcasts 360 individual radio signals, kind of like the spokes on a bicycle wheel.
Oh,
Yeah. So when a plane tunes into a VOR station, the system tells the pilot exactly which spoke they're flying on relative to that station.
so it gives you your exact direction from the station. And then the DME, which is the distance measuring equipment, does exactly what it sounds like.
Precisely. It calculates the time it takes for a radio signal to travel from the plane to the ground station and back.
Right.
So with VOR and DME working together, a pilot who's, stuck in the middle of a massive cloud bank knows exactly what direction they're heading and exactly how many miles away the ground station is.
That makes total sense. And the NDB that was mentioned in the sources.
That stands for non-directional beacon. It's an older, slightly simpler technology. It essentially just broadcasts a continuous signal in all directions.
Like a radio station.
Basically, yeah. And the instruments on the plane simply point an arrow toward the station. It's a critical redundancy. If the complex systems fail, you still have a reliable beacon to home in on.
Which brings us to the ILS, the Instrument Landing System. I've always imagined this one as like an invisible banister that the plane just slides down when the pilot can't see the runway.
That is actually a brilliant analogy.
Yeah.
The invisible banister.
Thanks.
Because that's exactly what it does. The ILS projects 2 highly focused radio beams up into the sky right from the runway. One beam gives the plane its horizontal alignment.
So keeping it perfectly centered on the runway.
Right. And the other beam gives it the vertical alignment, which is known as the glide slope. If the pilot just keeps their instruments centered on both of those beams, the plane essentially slides down that invisible banister right to the tarmac.
Wow.
And Dumar was responsible for modernizing and installing these massive systems at major international hubs, working as an advisor for the Macadia International Airport Autonomous Institute.
Okay, so he's building these lighthouses and invisible banisters. But the sources also mention he directed the Ionospheric Observatory project in Merida, and he ran something called the Radio Emission Monitoring System, or SICOTR. Now, I understand building a radar dish, but why does an aerospace engineer need to run an ionospheric observatory? I mean, that sounds like pure astronomy.
It's a great question, and it really speaks to the broader environment that these systems operate in. So the ionosphere is a layer of the Earth's upper atmosphere that is just packed with electrons and ionized atoms.
Okay.
For radio engineers, the ionosphere is basically a giant ceiling that they use to bounce high-frequency radio signals over the horizon.
Because the Earth is curved, so you can't just shoot a signal straight.
Exactly. But that ceiling isn't solid. It changes. It fluctuates based on solar flares, space weather, even just the time of day.
Oh, wow. So if you don't monitor the ionosphere, you don't actually know how your radio signals are going to bounce.
Exactly. You could be trying to communicate with a plane 500 miles away, and if a solar flare disrupts the ionosphere, your signal just punches right through into space instead of bouncing back down to the aircraft.
That is terrifying.
Right. So directing that observatory meant he was mapping the very medium that all these safety systems rely on. And SICOTR, that radio emission monitoring system, goes hand in hand with that. SICOTR acts as the traffic police for the radio spectrum.
Right, because if someone on the ground starts broadcasting like a pirate radio station or a massive commercial signal on the exact same frequency as the instrument landing system.
Catastrophe.
Yeah, that invisible banister we talked about suddenly vanishes. Or worse, it gives the pilot the wrong angle.
Precisely. He wasn't just building the systems. He was actively policing the invisible spectrum to ensure no interference could trigger a disaster. He also served on the expanded committee for implementing geostationary satellite systems.
Right, specifically dealing with VSAT and ISBN networks.
Yes.
And VSIT stands for Very Small Aperture Terminal, right? Basically those small satellite dishes that allow you to bounce data off a satellite in orbit rather than relying on ground cables.
Yeah, because in a country with incredibly diverse geography, you've got mountains, jungles, coastal plains. Running physical cables for aerospace communication is super vulnerable.
Oh, sure. A landslide cuts a fiber optic cable and suddenly a whole airport goes dark.
Exactly. So VST and ISBN networks create an incredibly robust, decentralized backbone. If the ground fails, the satellites just keep the data flowing.
Okay, so laying out the sheer technical complexity of this is mind-bending, but that raises a massive problem, at least in my head.
Well, what's that?
Building the central nervous system requires highly advanced technology, international vendors, and an unbelievable amount of money. The sources note Dumar was the special commissioner for the presidency of the Republic, specifically for the Air Court Institute, managing multi-billion-dollar budgets.
Multi-DN with a B.
Right. He oversaw the international bidding for radar systems nationwide and the commissioning of those ILS systems at airports in Barcelona, Marrakech, and Nueva Esparta State. And I have to pause here. Public infrastructure, international bidding, multi-billion-dollar budgets. I mean, in almost any country in the world, that equation eventually equals intense scrutiny, vendor lawsuits, or flat-out corruption scandals.
It's unfortunately very common, yeah.
Yet the documents explicitly state his administrative record has remained entirely unchallenged by any subsequent political administration for decades. How? I mean, how does one engineer survive shifting political winds without a single contract being torn up or investigated?
It's honestly the most remarkable part of his blueprint. And the answer is that Dumar used engineering principles to solve administrative vulnerabilities.
What do you mean by that?
Well, think about how a corrupt vendor operates in public bidding. They exploit the gray areas in a request for proposal.
Ah, right.
If the technical requirements are vague, a government official can easily justify selecting a favored vendor with inferior cheating technology.
Oh, I see where this is going. The math becomes the armor.
Exactly. Dumar wrote the technical specifications for these multi-billion-dollar bids with the exact same fault-intolerant mathematics he used to build the radar systems.
Wow.
He removed the gray areas entirely. He quantified every single metric signal latency down to the millisecond, failure redundancy rates, material tensile strengths.
So there's no room for interpretation.
None. When you construct a bidding process where a vendor must meet a literal mathematical threshold, the system disqualifies the corrupt bid automatically. A person doesn't even have to make a subjective choice.
That is brilliant. If a vendor's radar has like a 0.05% error rate and Dumar's spec strictly demands 0.01% based on international aerospace physics, they are just mathematically disqualified. There is no room for a bribe to fix that.
Precisely. And that is exactly why his record survived shifting political administrations.
Right, because the numbers don't lie.
When new governments came in and audited the books, looking for flaws or lucrative contracts to cancel, they found technical specifications so watertight they simply couldn't be argued with.
That's incredible.
The survival of his contracts across decades isn't just a testament to his personal ethics. It's objective proof of an airtight, rigorous procurement system. It's why there's a specific certification in his file from the Ministry of Transport and Communications.
Oh, the one commending his excellent leadership, responsibility, discipline, and dedication.
Yes. In the context of government infrastructure, that kind of certification is basically proof that his systems worked flawlessly.
But that begs the question, where do you even learn to build technical specifications that are that bulletproof? Which brings us to part 3 of our deep dive, the foundation, his academic journey.
And it is incredibly diverse.
It really is. He starts locally at LaSalle College in San Cristobal in Tucker State, but then he crosses the Atlantic. We are talking about doctoral studies in electronic engineering at the IMP in France, a Master of Science at ENSE-EIHT, also in France, a specialization in radar and radio aids at ENAC, again in France.
A lot of French education.
Yeah, and then he pivots to the United States to study technological engineering at Cal Poly.
If we connect this to the bigger picture, the combination of those specific educational cultures is really the secret to his problem-solving ability.
That's so.
Well, in the traditional French engineering system, places like INP and ENAC, the focus is heavily weighted toward profound theoretical rigor.
Okay.
You spend an immense amount of time with advanced calculus, theoretical physics, and deeply logical proofs. You don't just build a machine, you mathematically prove why the machine will work under any condition before you ever touch a single wire.
Right. It's about mastering the underlying laws of the universe first.
Yes. But then he goes to Cal Poly in California. And Cal Poly is famous globally for its learn by doing philosophy.
Very different vibe.
Totally different. The American engineering approach at that time was incredibly pragmatic, very hands-on, and focused on rapid technological application and hardware integration.
So he essentially fused the two. He could stand at a blackboard in Paris and mathematically prove the signal propagation of a radar wave, and then fly to California, pick up a soldering iron, and actually build the circuit board to catch that wave.
Exactly. Theoretical rigor meets pragmatic execution. It creates a uniquely adaptable mind. And what's truly impactful is that he didn't just hoard this elite cross-cultural education.
He brought it back.
Right. He brought it back to Venezuela and translated into a curriculum that could scale across a whole nation.
He basically became an institutional architect. I mean, the sources detail how he was appointed by the Office of Planning of the University Sector to design the electronic engineering degree at UNET.
Yep.
Then, CANTV, which is the national telephone company, requested him to design their telecommunications engineering degree. And he pioneered the University Institutes of Technology, the IUT, under cooperation agreements directly with the French government.
It's massive.
He wasn't just building radar stations, he was building the generation of engineers who would run them. He didn't just climb the academic ladder, he came back and built a completely new ladder for the next generation of Venezuelan engineers.
Which earned him recognition in 2022 from the SFEIC for his bilateral France-Venezuela forums. He really created an educational pipeline that elevated the entire national standard of engineering.
So what does this all mean? This naturally leads to a bit of a timeline problem for me. Dumar is currently 77 years old. He has over 50 years of experience.
Right.
When we look at the modern tech landscape, the overwhelming mantra is move fast and break things.
Oh, absolutely.
We push software out in beta, we patch it later, we disrupt entire industries overnight. If the aerospace industry has spent the last 50 years relying on guys like Dumar to hold the line on safety and methodical perfection, what happens as that generation steps back? Isn't his approach considered a bit, traditional now?
That is the pivotal quotient of modern infrastructure. Moving fast and breaking things is, well, it's an acceptable philosophy if you are building a social media app. If the app crashes, someone can't post a photo. It's a mild inconvenience. But when you are building the data centers that process global financial markets, or the satellite networks that coordinate autonomous shipping, or the AI systems managing municipal power grids, moving fast and breaking things, results in catastrophic real-world damage.
Yeah, people actually get hurt. The stakes dictate the philosophy.
Exactly. And this is why his perspective is actually more relevant now than ever. He operates from a framework of systems thinking that completely transcends any single era of technology. Consider this one detail from the sources. In 2014, Dumar received a special recognition from the Venezuelan Society of Endocrinology and Metabolism.
Okay, wait. I have to admit, when I first read that in the notes, I was completely thrown off. Endocrinology, like
Yeah.
the medical study of hormones. I couldn't figure out why a radar engineer was getting awards from medical specialists. But wait, hormones are basically just chemical signals traveling through the body, right?
They are.
They operate on feedback loops. If an organ needs something, it sends a signal, another organ receives it and responds. It's a communication network. Is this about systems thinking? Frequencies in the sky versus signals in the bloodstream.
You hit the nail on the head. When you understand systems at the profound level Dumar does, your insights transcend the specific hardware you are working on.
That's wild.
The principles that govern a stable, self-correcting national radar network are mathematically and logically identical to the principles that govern a healthy human endocrine system. He understands how vulnerabilities in a complex network, whether it's biological, digital, or physical, can be diagnosed and protected.
That makes total sense. It's also probably why the presidency of the Republic involved him in a special seminar on security and defense. He understands the architecture of vulnerability.
Yes, and it perfectly positions why his current professional offering is so vital for modern boardrooms. Organizations are quickly realizing that they simply cannot build a sustainable future on shaky, unaudited foundations.
Which brings us to the final chapter of this blueprint, the future. Currently, Dumar is offering his services remotely as a senior consultant and online technology advisor for boards of directors and global firms.
Right.
Now, a lot of people might think, why hire a 77-year-old consultant for a modern tech project? But looking at his resume, it's actually like hiring a structural engineer who spent 50 years building earthquake-proof skyscrapers to come look at the blueprint of your new experimental data center.
That's the perfect analogy.
Yeah.
You aren't hiring him to write modern code. You are importing an unblemished 50-year framework of risk assessment directly into your executive team.
Yeah.
His specific proposals are incredibly targeted. He offers technical and strategic auditing of technology infrastructure projects. He offers his proven methodologies for vendor evaluation and transparency in international bidding.
Which, as we established earlier, is basically his superpower.
Truly. And he's advising on the transition from ground-based to satellite-based navigation and communication systems. But the most striking element of his proposal, to me at least, is his offer to provide ethical and technical mentorship for high-performance engineering teams.
Here's where it gets really interesting. I found that fascinating because we rarely talk about ethics and engineering in the same breath. We focus on innovation and speed.
Constantly.
But you can teach a young engineer the software syntax easily enough. How do you teach them the moral courage to stand up to an aggressive vendor? Or, the discipline to tell a CEO that a multi-million-dollar launch has to be delayed because the redundancy audit failed? It's like having the Yoda of aerospace infrastructure on a Zoom call to audit your project.
You teach it through mentorship. You teach it by connecting that young engineer with someone who has actually walked that path, faced those exact pressures from politicians and executives, held the line, and survived with their reputation entirely intact.
Yeah.
You show them that integrity isn't just a nice concept. It is a vital operational necessity for long-term success. So I guess I'd ask you, what stands out to you about the idea of ethical mentorship in engineering?
It's just so crucial, and it ensures that the invisible systems we rely on every day stay reliable. Let's quickly recap the journey we've taken through this incredible blueprint today.
Sure.
We started by exploring the mechanics of the invisible hand, the VORs, the ILS banisters in the sky, and the ionospheric mapping that makes modern aviation possible. We analyzed the mechanics of public procurement and how mathematical precision in a contract can serve as an impenetrable armor against corruption, which allowed multi-billion-dollar infrastructure to survive decades of political turbulence.
We also looked at how combining theoretical French mathematics with pragmatic American engineering creates a uniquely powerful problem solver, and how that knowledge was scaled to create entire engineering degrees in Venezuela.
And finally, we saw how that half-century of systems thinking whether applied to radar networks, national defense, or even the human endocrine system, is currently being offered to guide the modern digital boardroom through high-stakes technical audits and ethical mentorship.
It's an extraordinary career, and it leaves me with an important question for you to consider as we move forward.
Let's hear it.
We are currently racing to build the next generation of invisible infrastructure. We are deploying massive artificial intelligence networks that will write their own code, sprawling global data clouds, and autonomous systems that will dictate everything from our finances to our power grids. As we increasingly remove the human element from the execution of our technology, will we ever be able to program moral courage and integrity into an algorithm?
Oh,
Or
wow.
will we always, fundamentally, need a human architect with a 50-year ethical horizon sitting at the top to hit the brakes?
That is a phenomenal question. Can an algorithm ever replicate the quiet integrity of a seasoned engineer? That is something I really encourage you to mull over on your own. Next time you're flying through those dense clouds, take a moment to appreciate the invisible math and the integrity of the people who built the systems keeping you safe. Thank you so much for joining us on this deep dive. Keep questioning the world around you, keep exploring how things really work, and keep learning. We'll see you next time.